Bridges, they've always been feats of engineering, but smart bridges, that takes innovation to the next level with advanced technology and cutting-edge design. For today's video, I'm going to count down 15 of the most incredibles. Number 15, the Øresund Bridge. The Øresund Bridge is a bridge-tunnel hybrid that connects Denmark and Sweden, serving as a vital transportation link between the two countries. Stretching nearly 5 miles from the Swedish city of Malmö to the artificial island of Peberholm, the bridge transitions into the 2.5-mile Drogden Tunnel, leading to the Danish island of Amager near Copenhagen. Completed in 2000, the Øresund Bridge was designed to address long-standing inefficiencies in transportation and improve border mobility. But beyond its primary function as a road and rail connection, the bridge incorporates some advanced technologies that makes it one of the most intelligent infrastructure projects in the world. The structure carries a critical data cable that supports internet communications between Central Europe and structural health monitoring systems to ensure the stability and long-term functionality. Those systems were specifically designed to address oscillations in the bridge cables, ensuring the structure can withstand any stressors while maintaining its capacity. The transition at the island serves multiple purposes. It allows ships to pass through the unobstructed Drogden Strait, maintains air traffic clearance for nearby Copenhagen Airport, and it minimizes environmental and visual impact on the area. The bridge's towers, standing 670 feet tall, support the weight of both road and rail traffic, while the underwater tunnel ensures uninterrupted navigation. Number 14, the Rion-Antirian Bridge. The Rion-Antirian Bridge, officially known as the Charleos Trikoupis Bridge, is connecting the town of Rio on the Peloponnese Peninsula to Antirio on mainland Greece. Spanning the Gulf of Corinth, this cable-stayed bridge stretches 1.8 miles and stands as a transportation link in western Greece. It was opened on August 12, 2004, just ahead of the Athens, and ensures that the piers remain stable, despite the loose substrate. High wind speeds, which frequently exceed 70 miles an hour in the strait, posed another design consideration. To counteract wind forces, the aerodynamic fairings were added to the bridge deck to reduce drag and stabilize the structure. These spiral scruton strakes were also installed on the cable stays to minimize vibrations caused by wind. Over 100 sensors are distributed across the bridge to track seismic activity, wind behavior, structural strain, and environmental changes. 3D accelerometers measure vibrations on deck, pylons, and cables, while strain gauges and load cells monitor the tension in the stay cables. Temperature sensors, too, monitor freezing conditions on the deck, ensuring traffic safety during cold weather. And additionally, 2 weather stations gather real-time data on wind speed, direction, temperature, and humidity, feeding this information into an integrated control system. Number 13, the Gateshead Millennium Bridge. The Gateshead Millennium Bridge spans the River Tyne, lingering full accessibility for disabled users, with a slope no steeper than 1 in 20. These constraints shape the design into its final form, a tilting bridge capable of providing clearance for vessels while preserving seamless pedestrian access. One of the cool features of the bridge is the tilting mechanism. It's powered by 6 hydraulic rams, 3 on each side. During operation, the supporting arch lowers while the pedestrian deck rises, forming a 40-degree angle and providing 82 feet of clearance for boats. The entire tilting motion takes about 4 minutes, with the bridge rotating at a speed of about 18 millimeters per second. Now, despite the speed of the movement, the hydraulic system is remarkably energy efficient, costing just a few pounds per opening. As the bridge rotates, any debris on the deck naturally rolls into traps located at either end. At night, the bridge transforms through an intelligent lighting system designed by Jonathan Spears & Associates. White lights illuminate the structure on weekdays, while colored displays brighten the weekends. Red and green LEDs are integrated into the system to signal bridge river delta. It connects those 3 major cities, Hong Kong, Zhuhai, and Macau, and it opened in October of 2018. The bridge was designed to address growing regional transportation demands and enhance the economic connectivity in the region. The idea for the bridge emerged in the early 2000s as a solution to improve transportation efficiency. Before its construction, travelers and cargo had to rely on ferries or significantly longer land routes. The bridge reduces travel time between Hong Kong and Zhuhai from just 4 hours to 45 minutes, streamlining the economic and logistical operations there. The bridge section spans 14.2 miles, while the undersea tunnel stretches 4.2 miles between 2 artificial islands. These islands, known as the Blue Dolphin Island and the White Dolphin Island, were designed to support the tunnel structure and ensure minimal disruption. Sensors embedded throughout the structure monitor activity, weather patterns, and structural integrity, allowing for predictive maintenance and immediate response to hazards. The bridge also uses adaptive lighting systems to ensure your visibility in white dolphin species. Number 11. Jindo Bridge. Jindo Bridge, located in South Korea. It's a pair of twin cable-stayed bridges that connect Jindo Island to the southwestern tip of the Korean peninsula near Haenam. The original bridge, completed in 1984, was Korea's first cable-stayed bridge, while the second bridge, constructed in 2006, was built to accommodate increased traffic demands. These bridges are notable for their impressive physical structure, but also for their integration of cutting-edge smart technologies. The addition of a second bridge in 2006 was a response to the rising traffic volumes, ensuring smoother traffic flow while also providing structural redundancy. Together, the two bridges meet essential transportation needs. The integration of smart tech has revolutionized the role of the bridge from a simple transportation structure to a hub of technological advancement. In collaboration with the University of Illinois at Urbana-Champaign and the University of Tokyo, a network of 113 iMote2 wireless sensors with sources. The implementation of smart tech on the Jindo Bridge addresses several key challenges for civil infrastructure. Continuous structural health monitoring significantly reduces the risk of sudden failure. Additionally, the data-driven approach generated by the monitoring system improves maintenance efficiency, ensuring its stability during high winds and adverse weather. Moreover, the smart systems improve traffic management by optimizing vehicle flow. Number 10. Queens Ferry Crossing. The Queens Ferry Crossing. It's a cable-stayed road bridge located in Scotland, connecting Edinburgh at South Queens Ferry to Fife at North Queens Ferry across the Firth of Forth. Spanning 1.7 miles, the bridge is a significant modern infrastructure project designed to ease traffic congestion while also addressing some specific environmental challenges. Completed in 2017, the Queens Ferry Crossing stands out not only for its size and design, but also for its use of advanced technology that make it one of the most sophisticated bridges in the world. The bridge was conceived as part of the Forth. Most of the iconic Forth Bridge ensures that it performs part of a critical network linking central Scotland to the northern regions. But what truly sets it apart from traditional bridges is the integration of smart tech aimed at improving safety, reliability, and operational efficiency. Wind is a constant challenge for bridges in Scotland, and the Firth of Forth is known for its unpredictable and strong winds. The system they use ensures that traffic remains uninterrupted even in extreme weather, which would otherwise cause significant disruptions. The sensors play a critical role in preventing issues like ice accumulation, which did lead to the closure of the bridge for the first time in February of 2020, 30 months after its opening, due to ice falling from the towers onto the carriageway. The automated wind shielding, for instance, allows the bridge to remain operational in conditions that would have led to closures on older structures. The temperature sensors further ensure that the structure can withstand the freezing temperatures common in Scotland during the winter. Number 9. The Akashi Kaikyo Bridge. The Akashi Kaikyo Bridge and serves local and long-distance traffic. The 1995 Great Hanshin earthquake tested its seismic resistance before it was finished. More than 100 contractors worked on it. Engineers equipped the bridge with wind, seismic, and structural health sensors to keep track of stress, wind conditions, and seismic activity. These sensors allow immediate adjustments and help predict how the bridge behaves in severe situations. A dual-hinge stiffening girder system also lets it withstand wind speeds of up to 178 miles an hour, or about 286 kph, and earthquakes as strong as magnitude 8.5. This design spreads forces across the structure, reducing any strain, and tuned mass dampers further control any oscillations by countering resonance. Deep underwater caissons support the tower in an area with strong tidal currents. The Great Hanshin earthquake caused a slight shift in the towers, so builders adjusted the central span. That flexibility became a key design factor in keeping the bridge stable. Temperature shifts on the tech and art, most notably through the Moonlight Rainbow Foundation, which holds the Guinness World Record for the longest fountain bridge in the world. The bridge itself is a vital route for vehicular traffic, but it also serves as a major landmark and tourist attraction. With a length of 4,905 feet and a width of 82 feet, the bridge is designed to facilitate not only daily commuting, but also public events and entertainment. The Moonlight Rainbow Foundation, inaugurated in 2009, is a display that features 38 water pumps and 380 nozzles capable of releasing up 190 tons of water per minute. The fountain operates about 5 to 6 times daily from April to October, and it's designed to recycle water to ensure some eco-friendliness. The water is shot out over distances of up to 140 feet horizontally and 65 feet vertically, making the display both a visual and environmental feat. The Bompo Bridge's integration of aesthetics and function served the challenge of transforming a transportation infrastructure into a cultural space. The panels generate enough electricity to power up to 50% of the energy required by the station, reducing its carbon emissions by an estimated 500 tons annually. It was originally built in 1886. The bridge has been a key feature in London's transport system, serving as both a railway station and a bridge. In 2009, the bridge underwent a major overhaul. The wrought iron structure was dismantled and rebuilt with a new roof equipped with solar panels. The roof spans over 64,000 square feet. It's roughly the size of 23 tennis courts, and it's capable of producing up to 1 megawatt of electricity on a sunny day. The solar panel system was designed to meet the high energy demands of the railway station. With the ability to generate that much power per year, the system provides enough energy to make approximately 80,000 cups of tea each day. While that renewable energy not only powers the station, but also helps reduce reliance on traditional energy grids. The solar panels were installed in phases over 2 years, and they were carefully timed to avoid interference with the 2012 London Olympics. And given the location of the bridge, there were logistical challenges. This pedestrian swing bridge spans the River Hull, connecting the city's old town to an industrial area and planned housing development. The bridge is shaped like an apostrophe when viewed from above and features a cantilever design that allows it to curve upwards to accommodate boats of varying size. Its pivot point is a massive 53-foot hub, which supports the 1,000-ton structure as it rotates. The bridge has a capacity of about 1,000 people per crossing, making it an impressive feat of design and an essential part of the local infrastructure. But what makes the bridge smart is how it integrates modern tech to make the bridge functional for pedestrians and cyclists while solving the problem of accessing the river without disrupting any traffic. The use of these sensors and automated systems help monitor and control the movement of the bridge, ensuring that it opens and closes only when necessary. The bridge has a low operational speed, which reduces risks and creates an added layer of safety. The scale-lane footbridge solves a problem by allowing pedestrians to stay on the bridge while it opens for boats. A solution. The bridge addresses several challenges while integrating technology and sustainable practices to create a unique infrastructure solution. With a length of 1,720 feet, it features a 780-foot-long main span, and this design features a 180-foot-tall pentagonal-shaped tower, which serves as the focal point of the bridge's distinctive aesthetic. One standout feature is the use of Freycinet multi-tube saddle technology, which allows for cables running from the deck through the towers and back down. This design not only ensures stability, but contributes to a cleaner, more streamlined bridge profile. The bridge is equipped with advanced LED lighting that reacts to real-time river conditions, and the system changes color and intensity depending on the factors such as Willamette River's temperature, the depth, and speed. For example, the base color of the lights is determined by the water temperature, while secondary patterns are based on the river's depth and current speed. This not only creates a visually captivating effect, but it also serves as a representation of the river's state. In 2019, TriMet further enhanced. Number 4. Smart Bridge of Eindhoven. The Smart Bridge in Eindhoven shows how new materials and technologies can reshape traditional infrastructure. It's part of the Smart Circular Bridge project in the Netherlands and highlights the future role of biocomposite materials. Built in Almere near Eindhoven, it spans 150 feet or 46 meters. It's the first of 3 pedestrian and cyclist bridges made from a flax composite. This is a renewable material that replaces steel and aluminum. Flax grows quickly and is widely available. The bridge has 80 sensors that track strain, vibrations, temperature changes, and moisture, and this data streams into a real-time public dashboard that helps researchers analyze performance under varying loads and conditions. The system allows for early detection of possible issues. It tracks how wind and heavy use affect the bridge, showing how flax composites hold up over time. Flax fibers, bioresins, and polyurethane foam blocks form a life by giving engineers insight into changing conditions. But beyond its function as a walkway and a bike path, it also serves as a test for larger biocomposite projects. Researchers hope to use these materials for walls, columns, and beams. And early results suggest bigger structures with longer spans and heavier loads may be possible. Its focus on sustainability, new materials, and real-time monitoring sets it apart. Instead of steel or concrete, the Smart Bridge uses a more eco-friendly approach that may guide future construction practices. Number 3. The I-35 West St. Anthony Falls Bridge. The I-35 West St. Anthony Falls Bridge crosses the Mississippi River in Minneapolis, Minnesota, carrying Interstate 35 West traffic. This 10-lane bridge opened in 2008 to replace the previous I-35 West Bridge, which collapsed in 2007. The Minnesota Department of Transportation pushed for quick planning and construction to restore a key highway. Despite the tight timeline, the bridge features advanced smart technology to monitor temperature, strain, and stress in real time. And experts at the University of Minnesota analyzed this data to track performance under different loads and weather, with anti-icing systems that detect slick conditions and sprays de-icing chemicals, limiting any ice buildup and cutting down on extra maintenance. Plus, energy-saving LED lights brighten the deck and the architectural elements. Real-time monitoring flags signs of wear or damage, allowing early fixes and reducing long-term costs. That concrete mix includes slag and fly ash to lower any carbon output and reduce water and chlorine penetration. TX Active concrete sculptures convert harmful particles into less toxic substances and stay clean with minimal upkeep. Instead of relying on standard materials and methods, the bridge combines smart sensors, self-cleaning concrete, and an automated anti-icing system. This approach supports durability, safety, and responsible engineering. Number 2. Slauerhofbrug. Located in the city of Leeuwarden in the Netherlands, the Slauerhofbrug bridge design allows the road section to be completely separated and raised 10 times a day, typically for passing boats. The mechanism that powers this unique movement consists of 2 hydraulic cylinders located within the pylon, which quickly raise and lower the bridge. This allows the bridge to move faster and more efficiently compared to conventional drawbridges, which often take longer to open and close. With a 50-foot by 50-foot deck, the bridge can handle heavy vehicle and pedestrian traffic when closed, while its quick motion prevents any significant delay. This approach makes it an efficient and reliable system for busy waterways where frequent boat passage is required. This eliminates the need for manual operation and ensures that the traffic is impacted for only a brief period each time the bridge is raised. The structure itself is built from iron and steel, and its distinctive yellow and blue colors reflect the flag, giving it both a functional and symbolic significance. The vibrant colors and modern design of the bridge also serve to enhance the city's visual landscape. The Slauerhofbrug serves several key issues that are common in cities with. Completed in December of 2004, this cable-stayed structure serves as a critical link on the A75 autoroute, connecting Paris to the Mediterranean coast. Before the Millau Viaduct was constructed, the town of Millau faced significant traffic congestion, particularly during the summer months. Vehicles traveling between Paris and the southern coast would bottleneck in the narrow valley roads, causing delays and straining local infrastructure. After an extensive design competition, a multi-span cable-stayed bridge was selected for its ability to span the valley with minimal disruption. Construction of the bridge began in December of 2001 and was completed in just 3 years, an impressive timeline considering the scale of the project. The pylons were built using sliding shuttering techniques, which allowed them to rise 13 feet every 3 days. The tallest pylon, Pier 2, reaches 803 feet above its base, supporting a road deck suspended over 890 feet above the Tarn River. Despite the project's scale, construction was completed on budget, on time, and without any fatalities. But what truly Millau Viaduct solves multiple challenges simultaneously. It eliminates chronic traffic congestion in Millau, reduces travel times along the A75, and minimizes environmental disruption in the valley. Its combination of smart systems, efficient construction techniques, and environmental sensitivity ensures that it will remain both a durable and adaptable structure. Unlike conventional bridges, this viaduct is not merely a passageway. It's a carefully designed system capable of responding to environmental and operational changes in real time. Thanks for watching, everybody. I'll see you next time. Thank you to our channel members.